fine.
Yes, Soumyadeep, you had something to say. Your hand is raised.
Yes, sir. I was wondering, for attending this course, we'll get a certificate or something?
Nothing as such, but if you do require and you have attended all the sessions, I can probably give you one on my letterhead. So, because this is just it's not in the academic program as such, but
yeah.
So depending upon your attendance and participation, we can probably consider that. Yes.
Okay, sir. Thank you.
Okay, then I think we'll get started. So very warm welcome. And before I get going, I would request everyone who's not speaking to mute their microphones. I request anybody else from with an IIC ID who can let the guests in to do that so that I can get going. There's so many people who keep coming there, so I need to admit them from the lobby. So anybody, those of you who are from IIC, you are all able to do that.
I'll do it. Sir, I'll do it.
Thank you so much.
This is Soumyadeep. I'll do it. Yes, sir.
Excellent, excellent. Okay. So very warm welcome to Professor Dr. Amar Garg. We're really privileged and honored to have him with us. As you know, and many of you have looked through his CV, which is available on the files in this team. He has a tremendous experience, and this is both academic as well as industrial. And he's going to be essentially talking about what he's worked on, so which makes it all the more significant. I hear some noises. Can everybody mute their microphones, please? Yeah, thank you very much. He has had an 18-year academic career in IIT Bombay before his education at IIT Kanpur. Was also related to aerospace, and apart from that, more significantly for today's talk and for this entire series, you would see that it's his experience with Boeing. You see a Boeing T-shirt over here. 105-year-old institution with which IISc, which is again a 112-year-old institution, has had a very long association with. Many of our colleagues have had long partnerships for research collaborations. And in fact, IISc is one of the 5 strategic partners of Boeing. And in that sense, we have done a lot of cutting-edge research towards some of the futuristic Boeing projects. So it's like a homecoming for Dr. Amar Gerg when we invite him to give this talk at IISc. And this similar kind of a series of courses he's given to pretty much all the leading aerospace ecosystem players in India, like ADAD and a few of the IITs. And I'm sure the kind of feedback we have got from some of the people who have attended that, it's going to be a tremendous value booster for us. Because he's been part of a big group of people who have converted what is called a dream to a Dreamliner. And though his contribution is to the movable trailing edge, abbreviated as MTE, which he would be talking about very shortly, each and every component here makes a huge difference. And many of you are working in the field of composite materials as well as structures, but we rarely touch upon in academia the certification, and that plays a very critical role in the eventual acceptance and seeing what you work on, not just remaining in a paper or in a thesis, but actually on a flying structure. And that gives a kick to you far bigger than anything else. And I'm sure some of you who are already graduates of IISc very kindly, Dr. Gerg let us to include and involve a few of our alumni as well. and some of you are already in the aerospace industry, and you know the kind of importance that this particular thing has as far as certification is concerned. Because just when we're working on research, we are tending to talk about various things, many of which might be too futuristic, and what is applicable currently is that which can be certified. And there are lots of constraints, and those constraints we need to look at right from the beginning in the design stage, right from the preliminary stage, so that we are not in for a rude shock, having worked on it, invested so much of our time, energy, and efforts towards this whole process, and eventually seeing that it's not actually ready to be applied. So how can you increase the TRL levels, the technology readiness levels of all of these things that you work on, and make sure that it's applicable on an actual flying structure sooner than later. So it's with this small introduction that I'd like to invite Professor Dr. Gerg. He is the way he has structured this is he has shared some of his lectures, and you would have access to that. We are also recording this, so some of you students who might have an internet issue, if you're working from home especially, and you miss a portion of it and rejoin later, you can always go back to those recordings to see what you have missed, or just for a review or whatever. And so once again, I thank Professor Gerg for this voluntary service, because usually we think that only things which are expensive are of value, but the most important things like our own life or even the air we breathe is free. And so we don't recognize how important the free things are. So in this sense, it's the complementary seva that Dr. Garg is doing by sharing his enormous rich experience. There's also a conference paper which has come out of his work on the MT along with one of his colleagues. And to be able to share that for free is indeed of great, it's a great gesture. And I'm sure all of us are going to benefit from it for a fairly long period of time. And he would like it to be interactive. So if you have any genuine questions, do raise your hands, and you can, when he lets in, you can probably ask your questions, doubts, or suggestions, and we can take it forward. So without much ado, I also would like to probably point out that apart from the 32 years that he spent at Boeing, he's also been for 2 years at NASA Ames Research Center, 1 year at Cranfield Institute of Technology in England. And because of that connection with one of his classmates there, that we are able to take this forward. That's how we got connected in the first place. And also he's been delivering part-time lectures at RMIT, one of the leading institutions for engineering and technology at in Australia, in Melbourne. With this brief introduction, because I can go on saying many things that he has done, but in any case, he's going to share that work and use that as the building block to explain various aspects of the certification. You might think it's just the movable trailing edge that he's going to be talking about, but it has a lot of significance and relevance for any other aerospace structure as well, which is made out of composites. It's like saying, if you have gone to the ocean and say, I have seen the ocean, it doesn't mean you have seen every drop of the ocean, but you still say that you have seen the ocean. You might go to the beach and say you've seen the beach. You might not have seen every grain of sand in the beach, but you still can claim that you have seen the beach. So it's like that. Through this small building block of a mobile trailing edge, which makes the aircraft far more efficient in all its regimes of flight. Because by moving the trailing edge, you're essentially changing the overall shape of the wing cross-section or the airfoil, and therefore making it either optimal or near optimal to the various flight or flying conditions that it flies in. So in that sense, it's a huge contributor towards various other aspects, like, for example, by making it efficient in all flight regimes, you're drastically reducing the fuel consumption, and therefore reducing the pollution, reducing the costs involved. So it has economic advantages, it has ecological advantages in the long run. So you can see that it's tremendously beneficial in various ways. And so I really am happy that Dr. Garg could spend some time with us. I see a lot of colleagues who are working in the composites field are also joining apart from the students. So I'm sure we will benefit from this and take it forward from there. So as I said, it's interactive, so feel free to raise your hands, and then Dr. Garg will let you in to ask a question. Thank you very much, Professor Dr. Garg. Sorry for taking a little bit of time from your talk, but I thought it was essential to give this background and the importance of this particular field. So the floor is yours, please. Dr. Garg, you might be muted. Can you hear me?
Thank you first, Dinesh, for introducing myself to your students and about the topic. I think it's a great opportunity for me to share my experiences with the students. I know IIT Bangalore has been the pioneering institute in India for the aviation, and most of my colleagues at IIT Bombay faculty, they were graduates of IIT Bangalore at that time, and I know lots of old friends from IIT Bangalore. Okay, now,
Dr. Garg, may I request you to share your video so that these people can see you for a while?
oh, I'm sorry, I don't know this. Is it okay now? No.
Maybe it'll take a second. Is anybody able to see Dr. Garg's video?
No, not yet.
It's not.
Not yet.
I'm just clicking that. It's not. You can share video when you are done screen sharing. Oh.
Oh, okay. So it doesn't allow both. Okay, well, that's fine then. Okay, not an issue. Please go ahead. Sorry for the interruption.
So I can start. Okay, can you just see my slide presentation?
Yes,
Dr.
yeah,
Garg.
please go ahead.
Okay, so as you know, the topic for this discussion is certification philosophy of composite aircraft structures. And as Professor Dinesh has highlighted, my example comes from the movable trailing edge structures, but nevertheless, the certification philosophy, whether it's a movable trailing edge or whole of the aircraft, philosophy is similar, the same. And I think that is because I had worked on the movable trailing edge within this company when 787 was just starting, in fact, right in the beginning. And so that's the example which I chose. And also I had presented a paper with my colleague in one of the SMP meetings, which I have taken the material from. So, okay. So I just want to declare this because the reason being that I've been employee of the Boeing, and of course we are bound by our agreement with Boeing, no disclosure agreement that I can't give any information about the Boeing, which is confidential or not in public domain. And that's why I'm just declaring all contents in this presentation are based on the materials in public domain. All discussions or conclusions or the opinions of presenter and not endorsed by any aircraft manufacturer or any organization. And it's only for your own use, not for publication, the material in it. Okay, introduction. So certification philosophy of commercial composite aircraft structures with an emphasis on 787 movable trailing edges. That's what I said. And this is a paper type. I won't go. Certain references which I thought are interesting to highlight. Of course, the first is a paper from SMP. And second one is again, is the paper from Boeing on 777 empennage certification approach, which was presented at ICCM 11 by Alpha Set and others. And they are all retired from Boeing now, of course. Alpha Set was a great person in composite structures at Boeing. Then third paper also, William, this is also from Boeing company. And By the way, you can all download this from internet free. ICCM 11, if you go, it'll give you it's a, freely available, all ICCM papers. This also is freely available. You can download from my Mill Handbook 17. I'm sure you people might have been familiar with Mill Handbook 17. Now this is known as a Composite Material Handbook. But the catch is, Composite Material Handbook, suppose you want to buy, it costs almost $2,500, all the volumes. Whereas Mill Handbook 17, which is the previous version of Composite Material Handbook, is available free to download from internet. And there's not much difference between the Composite Material Handbook, which is a revised edition, compared to this one. So I would advise you, if you have not got access to Mill Handbook 17, please download. It's very important because all the information about the composites, testing, design, certification that's contained, and data analysis is contained in these volumes. What you will get from books on composites, you will get all the information from this one. It's very handy. Of course, Michael knew, you might be familiar with this book. R.M. Jones has been a classical book. And some other NASA references. Again, all the NASA reports are freely available from NASA Technical Report Server. And almost every topic is covered by NASA. So I would advise you to just search through the NASA if you are not familiar with NASA Technical Report Server. It's very important or very useful server. Civil aircraft certification regulations, which are important. Again, everything can be downloaded from internet. So
You may please go ahead. I muted the noise from one of the participants.
I think Dr. Garg also is muted. Finish.
Dr. Gerg, can you unmute yourself, please? The noise was not from your end, it was from somebody else.
muted here. All right.
Yeah, we can now see it.
Okay, now, so I was just highlighting about these regulations. Part 23 is for small airplanes. Part 25 is for large commercial transport aircraft. 21 for procedures, certification procedures for products and parts, and so on. Now, another document which is very important here, Advisory Circular AC 2107B. What happened? This, when FAR 25 was written, mainly it was addressing the metal airplanes. But composite aircraft structures, when they came into picture, and there were certain differences for the certification strategy, then another advisory circular 107B was published by FAA, which provides the guidance. Of course, everything has to be following the Part 25, but guidance how to certify or how to develop the design data for the certification is written in this document. And I would advise you to download this. It's very interesting to read this document, AC 2107B. And then another one is 571D, damage tolerance and fatigue evaluation. This is also a very important document from the certification point of view for damage tolerance and fail-safe studies strategy. How do you meet those requirements? For military aircraft, JSSG 2006. Again, all these documents you can download. They are in public domain, freely. Useful document. I'll just put up certain links for the references, which you can use in order to download those documents. Okay. Okay, now let's consider what is certification. So certification of aircraft is a confirmation to its approved design, confirmation of manufacturing processes, and is in a condition of safe operation. This is all coming from Miller from those FAA documents, in fact. So, and basically, the certification ensures the safety of the product. The role of a regulator is to certify a product which is safe. So they ensure the safety for the public. So certification types: certification, design approval, production approval, and airworthiness approval. These are different certification types which are necessary when you are going to design and build the aircraft to get all these certificates from the regulators before you can sell the component or product. Design approval means design is approved and type certification is issued. And I'll explain you next slide what is type certification. Production approval means production is in accordance with approved design and quality system, and FAA will issue the production certificate, that is production manufacturing of aircraft. Airworthiness approval conforms to approved design and safe to operate. Okay, now TC, what is a TC? This is issued by the regulatory agency. TC signifies the airworthiness of approved design or type of an aircraft we manufacture. Now, suppose Boeing had to launch the project, that 787 when it was launched. Naturally, it would submit the application for the project to FAA. And of course, in the next diagram, I will show you all the procedure rather than discussing now. And of course, after the design is approved, they will issue a type certificate. Type certificate is the certificate for a particular design of the product or particular aircraft type. And no changes can, once TC is issued, no changes can be made to the design of the aircraft, any part, unless you can again apply for the regulatory agency to get a additional or type certificate, supplemental type certificate. TC once issued, design cannot be changed unless at least part of the process certification is repeated to cover the changes. TC reflects that the type design is in compliance with airworthiness requirements. Okay, design approval means type certificate, TC including amended and supplemental type certificate STC, or the approved design under product manufacturing approval, PMA, technical standard order authorization, letter of TSA design approval, or other approved design. Production approval means it is a document issued by FAA that allows the production of a product or article in accordance with its approved design and approved quality system, and can take the form of a production certificate, a product manufacturing approval, or technical standard authorization. Airworthiness approval, a document issued by FAA for an aircraft, engine, propeller, or article which certifies the aircraft engine, propeller, or article conforms to its approved design and is in condition of safe operation on this. So that means for a product like aircraft, all three certificates are necessary before the company can sell the aircraft. Type inspection authorization means TIA, which I'll show you what type inspection authorization is next slide. TIA is used to authorize official conformity airworthiness inspection and flight test necessary to fulfill certain requirements for TC, STC, amended TC, and amended STC. Now, so this is the flow chart which is important for the certification process. And this is the certification process, in fact. Manufacturer, application for TC, say Boeing for 787, applies for TC to FAA, airplane certification, specification report, and certification plan, which is submitted to me. Then regulator will assign a project number for that. Then once the project number is assigned, the manufacturer will start working on the design, fabrication methods, the material processes, and so on. And once manufacturer has done its work, it will submit the data to the regulator, which reviews the design, and manufacturer conduct a structural material and flight test after that. And once the regulator is satisfied with the design, the process, and certain material and structural test data, then regulator issues the type inspection authorization, and which I showed in the previous slide what it is, type inspection. That is an authority or that authorizes the manufacturer to perform the flight testing of the aircraft. So, and that flight testing which is performed by the manufacturer once TIA is issued, that is in presence of the regulator or their representative who will witness the flight test. And once flight test is satisfactorily done, then manufacturer will submit the test report data and final design package to the regulator, and the regulator will then issue TC, type certificate. And this is the process flow which is used for any aircraft project, whether it's a European or American. Okay, now for military certification, I don't have a flow diagram like that because there's no single flow diagram. And that's why certification of a military aircraft is generally a process negotiated between manufacturer and the regulator. A flowchart for the military aircraft would be different to civil aviation and is not provided here because I don't have access to that and there's no single flowchart. Okay, certificate, main elements of the certification. You have manufacturer and the regulator requirements. Design analysis, testing and evaluation, and the manufacturing. These are the three basic elements for the certification. And then, of course, the documentation, which is submitted to regulator, and product certificate. That's what we discussed in the previous slide, of course. Challenges for certification for composite compared to metals. Now, issue is, what is the difference between the certification of a composite structure and the metallic structures? Now, we know that there are certain differences between the composite materials. Like materials are heterogeneous. They are anisotropic, which really puts certain difficulties in the analysis of the structures because of anisotropy. While metals are isotropic, the analysis becomes easier compared to anisotropic materials. Environmental sensitivity, resins we know are highly environmentally sensitive, like suppose we are talking of the current composite materials which are used for most of the aircraft structures, which are cured at 350 degrees Fahrenheit or 180 degrees centigrade, the epoxies. They are sensitive to the temperature and moisture. And if we consider like a compression strength, compared to the room temperature at about 70 degrees centigrade, which is normally the operational temperature for which we design the aircraft, The degradation factor, which we normally would get, is almost 20% reduction in the compressive strength. So that's environmentally sensitive with the moisture and temperature both. Complexity of analysis, as I said, because of isotropy, it is sensitive to damages, and the damage types will be different to metallic structures. So we have to account for the differences between the metal and composite damages. One of the problems with the composites is the damage analysis is far too complex, and there is no deterministic crack like what we have in the metallic materials. We can study, okay, one crack growth will be there, and we can use like a Paris law in order to generate the crack growth law and predict the life. Whereas in composite, there's nothing like single crack. And usually we will discuss that in composite, we use the normally no growth of damage approach. Fatigue and damage tolerance. There are certain differences between a composite and metals when we try to assess the fatigue and damage tolerances. So we have to account for that, which makes the composite structure analysis more difficult. Damage growth predictions, modes of failure and failure criteria. Then modes of failures are different compared to the metals, and that's what makes it different for the analysis. Material reliables. Okay, now this is a very difficult issue for composites. In metals, suppose you want to design the aircraft using aluminum 7050, which is usually a common material for aircraft structures. You can get all the data from Millenburg 5. So that's in public domain. You don't have to do any testing in order to generate the basic reliables for the metal. Whereas in composites, every material is different. Every company will be using different materials. And no company will share the data. Like suppose Boeing has developed a particular material data. They are not going to share in the public domain with Airbus. Or Airbus, what they have developed, the data reliables for their material for composite, they are not going to share with anybody else. And there are numerous combinations of that because materials, resin, fibers, they could be different. Process of manufacturing could be different, so the data reliables change. So material data reliables, there's no single source of material reliables, and you have to develop your own material reliables for a material which is suitable to your structure, which makes it very expensive. Like I can tell you, during 787 program, and that's what I'll discuss, of course, and significant amount of testing had to be performed in order to develop the materials reliables. Processing composite materials, there are many processes which we'll consider in our lecture over here, like autoclave process, non-autoclave process. Lack of database, I just touched on that. Structure repairability is not, again, in composites, the repairability is more complex than the metallic structures. Large number of tests required in order to qualify the materials and develop the design reliables. Lightning strike damage protection, because we know the composites are not good conductor of electricity, and that is why lightning protection is required, and which causes certain difficulties in the structures. Bird strike damage. In metallic structures, the bird strike damage could be different to the composite structures, and that is what has to be considered separately. Galvanic corrosion in another area is another area which is different compared to metals. What happens, suppose you have a carbon skin and then you are interfacing the aluminum, fitting over that. Carbon to aluminum, what happens? Carbon causes galvanic corrosion. to the aluminum. So aluminum start corroding when in contact with the aluminum. Sorry, in contact with carbon. So in order to avoid galvanic corrosion between the carbon and aluminum fitting, you need certain protection between that. So normally the glass layer as a barrier film will be laid up, which separates the aluminum to carbon. Fire safety issues because composites will burn differently the aluminum. So it requires different considerations for the fire safety. Materials and fabrication process variations. So the purpose of this was to highlight that compared to the metals, there's many differences in order to develop the design philosophy for the composites and certify. And all these things, these items which are listed, are part of AC 2107B, which specifies what needs to be done in order to certify a composite structure. So preceding issues lead to additional requirements to certify aircraft composite structures. Usage of composites in aircraft. One of the key drivers for the use of composites. Now, one would ask, I have shown many of the difficulties of using the composite structures compared to the metal. Then why do we use composites at all? And the key to that is, of course, it does have advantages, and that is why now you see today's aircraft like 787 or Airbus 350, they have almost 50% of composites in the structure, because it leads to a fuel consumption reduction. So key drivers of composite usage is weight reduction, composite fuel efficiency for aircraft, which leads to cost saving to the airlines, and also it is environmentally friendly. If you can reduce the fuel consumption, naturally you will create less of greenhouse gases. Okay, motivation of composite usage in aerospace. Compared to aluminum, certain improvement in parameters, high specific strength and stiffness. We know that it offers very high stiffness and strength, low density, but higher stiffness and strength. Fatigue behavior will show fatigue behavior is better than metal for the composites. Minimized corrosion issues, aluminum corrodes where carbon doesn't corrode, so naturally it's an advantage. Reduced number of parts, you can integrate many of the parts, details possible, and which may save the cost, and also reduced number of fasteners. You can double the bonding of the structures, which reduces the fastener, and fasteners is a big cost to aircraft industry. So due to this, the result is lower weight, lower fuel consumption, lower maintenance, lower cost, increased cabin pressure, increased passenger comfort.
Dr. Garg, can I ask a question here?
Yes, sure.
Yeah, this is Amar Bhatt. I am from IIC, a colleague of Dr. Dinesh. Yeah, in this slide, the last point is not very clear to me. How does using composites help in increase cabin pressure?
Okay, now what has happened? We know that all historically the airplanes cabin pressure was maintained equivalent to 8,000 feet, and that is what the minimum. It was found that the human body could tolerate the pressure. So currently, if you travel in the aircraft cabin pressure is equivalent to 8,000 feet, which is around 8.25 psi.
I see. Okay.
Okay. Now, what happens with Boeing 787 program when they developed? They could reduce the weight of the structure, barrel, fuselage weight could be reduced by using the composites. And when they could reduce the weight of the structure, what they did, they could reduce the altitude of operation, that is the pressure equivalent to 6,000 feet. So currently Boeing has the pressure equivalent to 6,000 feet inside the cabin.
Okay.
That means the pressure is higher, not 8.25 psi, but maybe around 9.5 psi. I'll have to look into the ICAO table. So higher cabin pressure inside. And that was possible with this composite because we know the internal pressure of the cabin to outside pressure is low. So differential pressure will rupture the cabin walls. The structure has to be strong enough.
Yes.
And composites provided that strength compared to aluminum.
Okay.
So higher the pressure inside makes the body comfortable. Suppose pressure was equivalent to ground level, then we won't feel any problem during takeoff and landing as we feel currently when we are landing. Our ears
Yes.
feel some pain.
Yes.
Now that is what, when I have written this para, I have said increased cabin pressure, increased passenger comfort. So is it?
Yes.
Could I
Yes.
make?
Yes. 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 That answers my question. Yes. Thanks.
Okay, now this is just an example to show the impact of the composite materials, and I have taken this information from one of the NASA reports, which again these are Boeing people who had written quite some time back. So this is a Boeing analysis in public domain. Wing box and fuselage, when they were studying in 1980s, the composite structures, advantages compared to the aluminum. So NASA had funded lots of projects for Boeing, Lockheed, and you can go through NASA technical reports server and download these reports. They're very interesting. Lots of commercial aircraft studies which were done by these big companies all through NASA. So that's why they are all in public domain, NASA. I find NASA server to be very useful. Every day I search lots of reports from NASA and I get the information. Very useful. Okay, now, so in this slide, what I have shown, just taking for example, that the wing box panels, composite wing box and fuselage savings compared to aluminum when they had done this study. This was done for a large commercial transport. What with the saving? Of course, this is in 1980s, and today, of course, we have much better materials at that compared to that time, and savings would be more even. So what you see here, upper surface panel, 24%, lower surface, 49%, spars, 40%, 38%, panels and spars, fuselage shell and fittings, 21%. Overall, average, if I take almost, it could be almost like 25 to 30% average for fuselage, shell, and the wing panels, saving in the weight. So there's a huge saving using the composite materials. Okay, this chart shows, you might have seen this in many of the references, many places it's being quoted from Boeing. Now, what you see, 747, which was certified in 1969, only 1% composite was used, just some glass epoxy, not carbon at that time. 757, which was certified in 80s, 3%. 777, certified in 90s, early 90s, 11%. And suddenly 787, certified in 2010, 50% composites. So there's significant jump. Here, you have the fuselage, wing. Most of the structure is composites. Next slide will show that. So this is 787 aircraft, you can see, and almost all of the structure is carbon composite. And equivalent aircraft from Airbus 350 is also similar to this, which is, by the way, 53% composite. This is a chart which I've taken from one of the publications, presentations by Boeing or in ICCM. What it is just showing you, say these are the aircraft like 747. Oh, sorry, this is 777, sorry, quads. Oh, I'm sorry, 747, quads, 747. And these are like 77 aircraft, twins. But you see 787 lies over here in terms of fuel consumption per trip and fuel consumption per seat, which is considered to be 20% fuel saving to the airline, which is a big saving in terms of cost to the airlines. And so, of course, then passengers. Now, this has been possible by using the composites. It won't have been possible using a metal. This table, of course, is again on a Boeing website. You can see just showing the comparison between one aircraft version to another aircraft version. I won't go into the details of this. 787-8 was the first version, and then revised one 910 with the seating capacity going up. Okay, now let's discuss the 787. Anybody has any questions so far? No. Okay. You can always ask me anytime. Okay, 787 movable trailing edges. What are these movable trailing edges? Basically, they're the flaps, flaperon, and aileron, or trailing edge surfaces. They call them movable trailing edges. So you have inboard flap, you have flaperon between outboard flap and inboard flap, and then aileron. We all know the function of these details, and these are spoilers and the rigidity panel. Okay. Let me just show you this one. So empty structures, PSEs. What is PSE? Principal structural element. I'll show the next slide, the definition to make it very clear what is principal structural element. So therefore, like a primary structure or secondary structures, basically. This is secondary structure and this is a primary structure. But we call, rather than secondary and primary, we call them principal structural elements and non-principal structural elements. So these are principal structural elements like inboard flap, outboard flap, and aileron, and which are fastened rib skin spar structure. They're like a black aluminum, basically, when we designed them. And then these, to manufacture these composite parts, the resin infusion process is used rather than the autoclave process. Non-PSEs, flaperon, and spoilers. Flaperon is, of course, the stiffened structure where the spoilers are bonded sandwich structures and they are autoclave cured, not resin infused parts. Any question on this? No. Okay, I said what is principal structural element, which is like a primary structure. So definition per AC 25571D, an element that contributes significantly to the carrying of light, ground, or pressurization loads, and whose integrity is essential in maintaining the overall integrity of the airplane structure. Basically, suppose PSE fails, that means safety of the aircraft is jeopardized. And that is why you do not want the PSE to fail. Non-PSE, they are secondary structures, essentially, an element merely to provide enhanced aircraft performance. However, the failure of PSE, non-PSE, shall not jeopardize the flight safety. This will jeopardize the flight safety. Failure of PSE non-PSE is to enhance the performance of the aircraft. And that's the difference between these two. Okay, let's consider these individual components here just to highlight a bit more details. Of course, I couldn't show the internal details over here, but basically it has a ribs, spars, like a conventional aluminum structure, and facet. Inboard flap, single slotted, single segment type highly devices. The structure consists of multiple spars and ribs fastened to the skin. Skin's rib denotes leading edge and spars, solid laminate, carbon fiber reinforced plastics, and manufacturing process resin infusion. And these are metal fittings. Top tube. Similarly, the outboard flap, exactly same type of structure as the inboard flap. Skin, composite, metal fitting, carbon denos, metal fitting, oxtack. Aileron, similar. It has multiple hinges. There's no denos over here. And these are fitting and actuators both. Aileron hinge control surface used for low speed roll control, lift control during takeoff, and drag reduction at high speeds. Front and rear spars and rib fastened to the skins, skin spars and ribs, all solid laminates, similar to the flaps, and manufacturing process similar to the flaps, resin infusion process. I'll show those of you who do not have not been familiar with resin infusion process in my discussion in some of the slides I have got in this presentation. Flaperon, similar to the flaps in terms of the structure, is a hinge control surface between inboard and outboard flaps. Flaperon drives a hinge panel which is attached by linkage to the flaperon. And flaperon hinge panels provide roll control, high lift, and high speed drag reduction. Structure similar, multi-cell rib dominated structure with main and rear spars and manufacturing process, resin infusion process. Spoilers, total 7 spoilers on either side. Spoilers function as a speed brake and roll control, and also they droop down to control the gap between the spoilers and the flap for high lift performance. So spoilers are full depth honeycomb core sandwiched between front CFRP spar and the CFRP skin. So you have this carbon spar, carbon skins, and it is honeycomb sandwich structure. Now, the process to manufacture this is autoclave. One would ask, why not RI? Of course, you can't use for sandwich structure the resin infusion process. The reason being, if you try to use resin infusion for a sandwich structure, the core cells will get filled with the resin. And so that's why you have to use the autoclave process. Now, just I want to highlight sandwich structure. When I was working on the Airbus landing gear doors, I was in charge of a project resin transfer molding development process for the Airbus landing gear doors at that time, because we were manufacturing in early 90s. The Airbus landing gear doors for 330 and 340 were being made by Melbourne company, Boeing. And because at that time the landing gear structures were all sandwich, and we had to work on developing the structures using the resin transfer molding process. So the question was now, we can't use a honeycomb structure for resin transfer molding because all the cells will be filled with the resin and it will be like a solid. So in order to use the resin transfer molding for sandwich structure, we had to search for some kind of a foam material. Okay, so I looked into various types of foams and we got one foam, Roacel, from Rome, Germany. Well, you might be familiar with Roacel, if not. Roacel is a closed cell foam material. And we tried to use that in order to make the landing gear doors. It was just experimental, of course. So we designed with that. But unfortunately, what happened in the meantime, we performed some tests for hygrothermal sensitivity of the Roacel sandwich structure. And we found that the Roacel used to crack due to hygrothermal cycling. And that was a big setback at the time to our project. So halfway between that, during the project, we had to switch over to stiffened structures for RTM. So why I told this story about this, that really sandwich structures you can't make using the resin infusion process or RTM. This slide shows a typical flap in assembly line within Boeing Australia. So it's just a part of the flap you can see here. Again, because this was in the public domain, this picture I thought I'll show you. And as I described, the structure, it's fastened. So you have the one spar, another spar over here. This is a trailing edge. The fasteners running over here. And here they will be fitting what I showed in the slide. And so this is just a typical structure from outside. What you can see is it's like a black aluminum, like black aluminum when I'm calling is conventional aluminum structure with rib, spars, stiffeners, all fastened together. Just typical, I thought, typical stiffened structure. I'll show you here. Nothing great about it. Schematically, you have spars, dinos connected, and the trailing edge. Approach to certification. Okay.
Excuse me, sir.
Sure. Yes.
Sir, I would like to ask this aileron and this like principal structural elements. You said that resin infusion is used. So
Yes.
in resin infusion, the process was like resin transfer molding only, or it's other variants? I mean,
Well, a resin infusion process is similar to what your annual is using. In fact, basically, they are calling variety. What is it? Okay, exactly. Same process. There are different names. Some people call resin infusion. Of course, Boeing calls Capri, in fact.
Okay.
That was fuel pressure. But it's a VARTM, VARTM.
VARTM. Okay. So not So not with high pressure of resin, but by inducing the vacuum and
Yes,
using.
that's right. That's right. Resin infusion process is that because, in fact, when I was telling the story about the landing gear door development using a resin transfer molding, and we were using closed mold system at that time rather than the vacuum.
Okay.
So that was resin transfer molding with a closed mold system, solid mold.
Okay.
So this process, this is nothing but VARTM, vacuum assisted resin transfer
molding. Okay, sir. Okay, got it. Thank you.
Otherwise, closed mold system is very expensive, and then it becomes not feasible.
Yes, sir. Yes, right, right. Thank you.
Okay. Okay, now approach to certification. Certification approach is an integrated approach. I've not highlighted all the details over here, and there are many other considerations which go into the flow diagrams. I just put a few key elements for this. So you have the customer requirements, and you try to do the structural analysis, like suppose flaps you are designing, and using the customer requirements and the regulatory requirements, you would start working on a design details. And in order to do the design, of course, you would require testing and reliables, quality assurance, interaction, fabrication, process development, interaction with that, repair, maintenance, documentations. So these are some of the elements which are important for the structural analysis, but nevertheless, it's not the end of it. There are plenty more. It's very simplistic diagram I put. Okay, customer requirements like performance, operational loads, weight, geometry, cost. So these are performance requirements which you need to consider in order to develop your design. I thought, let me just put a table over here to highlight some of the important regulations for the structures design, which are key to structural analysis and design. Like loads, you have 25501, factor of safety 25302, strength and deformation 305, 307 proof of structures, material process 613, damage tolerance. This is very important, part 25571, and my main emphasis in this lecture would be 25571, and you will hear me naming this 25571 quite repeatedly because it's one of the most important regulation to which we have to design the aircraft structures. Lightning protection 25581, protection of structure 609, stability aerology 629, materials control 603, process control 605, and continuous airworthiness repairability 1529. In addition, hundreds of regulations per 14 CFR Part 25 shall be met in order to certify the product. Also, I just highlight, I have just put some details using 14 CFR 25 AC 2107B, which is the guidance for the aircraft composite structures, what it contains. So it contains the materials and fabrication development, material process control, manufacturing implementation, structural bonding, environmental considerations, protection of a structure, design values, structural details, proof of structure. How do you do the structural proof, static and the fatigue damage tolerance? So it provides the methods, damage tolerance evaluation, fatigue evaluation, combined damage tolerance and fatigue evaluation, proof of structure, flutter, and other aeroelastic instabilities, continuity worthiness, design for maintenance, maintenance practices, damage detection, inspection, repair, documentation, reporting, substantiation repairs, damage detection, inspection, and repair competency, various. And there are certain additional considerations like crashworthiness, fire protection, lightning protection, all that. Okay, I want to highlight, in fact, as I advised you, that you should download this document from FAA website and just glance through, you'll get a good feel what it contains. Okay, now design certification approaches. Certification of aircraft structure approaches. There are three types of approaches one could follow. One of these. One is certification by test, which is a point design approach, where It may be the initially, it may be the low cost, but in long term run, this costs much more. So generally, the industry will not use this approach. If the industry has to produce only one part, one component, one product, and they are not looking into any variation of that later on, then probably one could do that. But generally, the industry will use certification by structural analysis verified by test. Certification by analysis is also not recommended or not easily acceptable. It may be accepted only if enough confidence in the analysis exists. So you have developed the methods of analysis, and once FAA has approved all those methods of analysis, probably it might be easy to go through certification by analysis. But in spite of this certification by analysis, suppose you've got all the methods, all the processes which are based on your previous versions of the aircraft, and like Boeing say they have a lot of data available from the previous say, metallic aircraft, and they could always piggyback because they've got design handbooks and they can design the aircraft without performing the significant amount of tests for the metal aircraft. However, one can't avoid the testing. The reason being, I'll show you that it's mandatory for aircraft manufacturer to test the aircraft in fatigue. And that is a mandatory requirement that every aircraft has to be fatigue tested. When I'm saying aircraft, that new aircraft design, of course, not every aircraft which you are selling. So certification in structural analysis, this is the preferred approach by the aircraft industry, whether it's Airbus or whether it's Boeing, same. Okay, now here I've just highlighted a few points about each of these philosophy. Certification point design approach. Certification by testing the complete full structure, that is how you would perform the certification using point design approach. The allowance.
One quick question, Dr. Garg, if you.
Yeah.
Yeah,
sure.
when we talked about this fatigue testing, are we talking about the full scale fatigue testing of the entire aircraft assembled?
Yes,
or
that's right.
Are there tests on individual sub-components under fatigue before certifying?
The thing is, in order to achieve the confidence, you would do some certain subcomponent testing also. And then final aircraft that is required, this is mandatory now. Since I think 1998 or so, exactly, I don't know. I've got the date over here in my presentation.
Okay.
Since then, the aircraft has to be fatigue tested. And I'll show you the requirement. This is from 571B now.
Okay.
This requirement came after Aloha accident, in fact, and that's what we'll discuss. Aloha or Dan Air, one of them. So we'll discuss that actually. I've got that percentage in my the requirement. So certification by structural analysis. Hello, yes?
Hello. So while the long-term cost is not high in the certification by structural analysis verified by test, I mean the third one.
Yes. Third
why
one.
The long-term cost is not high, but it is high in the first one.
Yeah, the reason is here, what happens, suppose, like say Boeing, you have got a 787-8 version. So you have developed a lot of material arrivals, everything you have done that. And then you want to change the version of the aircraft. Now, if you have to change that version of the aircraft, then you are looking for another testing.
Yes.
If you have already developed all the materials reliables, then you require a simplified analysis and limited amount of testing in order to validate your design. But if you have not done enough of reliables, in this, what happens? This point design approach, you do not do significant amount of data or data reliables. It's only limited amount of data reliables which is done. And then you are testing the full aircraft in order to demonstrate certification.
Oh, okay, okay.
Whereas in this one, you have developed your analysis tools also, which is verified by the test. So for the future generation of the aircraft using the same materials, it becomes very easy to certify. So cost is reduced. Initially, the cost will be high in this one.
Oh, okay, sir. Thank you, sir.
So that's the reason.
Yeah, yeah. Thank you, sir.
Okay, certification by testing the complete full structure. So reliables in this case is limited reliables. Initial cost may be lower. Any change in design will require testing component again. And this is the problem with this one. Say 787 aircraft. When it was designed, now later on the companies, of course, will always try to improve the design, change this one part, another part, and then, but it doesn't mean the company has to retest all of the aircraft. Suppose they are changing the flap, one outboard flap which is designed, say, stiffened structure, and now the company decides they want to go for the bonding technology, and they've got enough confidence in the bonding technology. They don't have to then test whole of the aircraft. What they can demonstrate, because they've got enough data for those materials, they may have to do only limited amount of testing. So that's the advantage of that in long run. Okay, certification analysis verified by test. This is the preferred approach, as I said. So here you have an analysis, certification of structures. Testing, you do coupon element, subcomponent, component, using a building block approach to testing. And this is what we'll discuss. What is building block approach? So using this one, you develop reliables and analysis methods verification. Essentially, what you are doing in this method, you are still certifying by the analysis, but all that analysis has been substantiated by your test data. Same during 787 program, and we'll discuss it, of course, all the details when we are designing this component flaps, all the movable trailing edges. The process was new at that time. The materials were new. And so we had to develop the analysis tools and verified by the testing. Okay, now, so I said about the full scale testing requirement. This is what I've just written the para from 25571B, which says damage tolerance evaluation. This demonstration must be by full scale fatigue test evidence. Of course, there are many paragraphs over here. So this is a must now. The type certificate may be issued prior to completion of full-scale fatigue testing, provided the administrator has approved a plan for completing the required test. In that case, the airworthiness limitations section of the instructions for continued airworthiness required by 251529 must specify that no airplane may be operated beyond a number of cycles equal to half the number of cycles accumulated on the fatigue test article until such testing is completed. So this is the requirement now, that every aircraft has to be tested. Introduction to building. Yeah. Any question?
Yes, sir. So,
Yeah.
is the requirement that the full aircraft should be tested is required because we don't have enough confidence on the numerical simulations?
Yes, that is right. And of course, what happens with this widespread fatigue damage? This criteria came up because of the widespread fatigue damage. Damage is how they propagate from one damage, another damage. Suppose you have series of fasteners. Now one fastener is having a damage. Another fastener may have damage, and they may accumulate and join. Now, in order to find out about this, that is why, in order to get the confidence in this, FAA dictates the aircraft testing in fatigue has to be there. And this requirement came from after, in fact, I've got it. Let me just show when did this come. After Aloha aircraft failure, and we'll discuss these issuance 90, Amendment 96 for WFD, widespread fatigue damage. And this is what happened. So it's mandatory now for whole of the aircraft to be tested before certification, full certification.
Okay. So, sir,
Yeah.
Dr. One more quick question.
Sure.
When you say each aircraft is subjected to full scale fatigue, do we mean to say one from batch of 787, one sample full aircraft, or each manufactured?
No, not each manufacturer. How can we test whole the
That's what I was wondering. Yeah.
No. It's
one.
This clause clearly says what happens. All this testing is done only for the first, initial production aircraft.
Right.
Only one aircraft. Say like 787-8, the first aircraft, or maybe series of 3 or 4 aircraft they will make. One will be the flight test, or 2 will be the flight test. One will be the this fatigue test. Another will be static test, like that.
Yes.
Okay. Once that is approved, then no, because what you are doing, you are having the same material, same production process, everything to be the same. You don't have to test everything. You can't test everything, every aircraft.
No way. And
so
in case there is a small change, then perhaps we have to do that.
Well, now the thing is, then what happens? Suppose you're changing only a small part of the aircraft, then you will try to demonstrate that locally by subcomponent testing. You don't have to change again and test whole of the aircraft. Suppose they have changed. Suppose one of the flap design has been changed. It doesn't mean Boeing has to again perform the full-scale fatigue test of the 787 aircraft. No.
Okay.
These small changes are always there.
Right.
Boeing will keep on doing, and for improvement of it is what happens. The strategy of any company is, okay, initially you have done that work, you have designed the product, and you want to market it. Okay, it goes. And then you are trying to improve up the design, improve upon the production processes, because then cost-cutting thing comes into picture. Initially, because the company wants to sell the product, they don't have time to significantly optimize the designs and optimize the production processes. These changes would be done later on.
Right.
So whole of the exercise later on is to cut down the cost, production cost. So in order to do that, they might think of, okay, I've got so many ribs now in this structure. Can I reduce the number of ribs? Or can I make this change to reduce the weight, design cost, the fabrication cost? And that is what the versions will be there. So suppose you see 787 aircraft, which was certified in 2010 or 11. Today, there might have been many changes. compared to what it was. But those changes will be small.
Okay.
Okay, now building block approach. What is building block approach? The substantiation process using both testing and analysis in a program of increasing complex levels. So you have the testing, you have the analysis block over here. They're like a pyramid. So initially they start with a simple analysis, testing, and increasing in complexity to make the product to be efficient. And we'll discuss actually in each of these blocks what is there. So building block approach advantages: reduce program cost and risk while meeting all technical, regulatory, and customer requirements. Make design development process more effective in assessing technology risk early in the program. Cost efficiency is achieved by testing large number of small specimens and fewer full-scale articles. Using analysis in place of testing where possible also tends to reduce cost, reduces the probability of significant surprise in the end of this program service. Now, what happens if you now we are considering like a point design approach where you have a limited test data available, limited amount of work subcomponent, you would avoid some component testing. The result of that is sometimes, okay, you have tested the full component and the aircraft starts flying, is in the service or products in service. Later on, you may find there could be some issues with the product which you may not have been aware of because you have not done sufficient studies or you have not done enough testing. I've got a experience of that. Of course, I can't name the product because of the confusion, but we had a product which was put into service, and in service, certain issues came up after about a couple of years. And when you have the product in service with the issues, it becomes very expensive to rectify. The product had to be recalled, repaired, and it was a huge cost to the company. So, and that is why it's very important to follow the building block approach, or like a TRL approach, what Professor Dinesh was mentioning, technology readiness levels, different levels which are defined by NASA. So, building block approach to testing, which is a systematic way of obtaining the design information of the composite materials and structures and leading to testing coupon elements, subcomponent, and component level tests. So, building a block approach, factors influencing federal regulations, criteria, standard practices and procedures, validated allowables, design values, and analysis methods. Do we want to stop over here and just 5 minutes remaining before we close off? Any questions or any comments you'd like to offer to make the improvement for the next lecture?
Can I ask one of the questions?
Sure.
Yeah. When we talk about certification, we saw your presentations that there is certification of process, there is certification of manufacturing and all that.
Mm-hmm.
How about the raw material used for these fabrication process? For example, carbon fiber itself or the epoxy itself? Are there mandatory certifications, or do we accept the manufacturer's certificate?
What happens? We'll study that. I've got it here.
Okay. If you are going there later, fine.
Yes. Yeah. I'll be discussing how we certify that. So let's. But
yeah.
Yes, we have to do all testing and certify the material before we accept it. So yes, and that's what is part of the building block approach.
Right. Okay.
Okay.
Okay. Right.
Any other question? Anybody?
A general question. I don't know whether you would like to want to answer that or you don't want. There was, I remember, even in the newspaper, fleet of 787 were grounded, and I remember it as a power plant problem or the battery problem or something like that.
Yeah, that you might have read in the press media release.
Yes.
Yeah, there were some issues, of course, at that time. They were all sorted out.
Yes. How did it creep in? Did it? Is it because of any of the tests were not performed on this?
No, I'm not aware of that because I was not involved in that battery. There might have been some battery issues. But usually what happens when a product is put into service, there will always some minor issues coming up. It's difficult to envisage everything. And moreover, Boeing has thousands of subcontractors.
Okay.
So yes, all those things. When some issues come up, they sort it out. And I can tell you the industry, the safety is a primary goal and is one of the maximum safety standards if it follow is in aircraft industry really.
Right.
At every step.
Okay, thanks.
Yeah.
Sir, in continuation with the previous question regarding the material selection, I would like to know, like, for example, since we are mostly using CFRP, like involving carbon fabrics. So normally what happens is sometimes, suppose if we specify the carbon fabric, with all the parameters, including the GSM of the fabric. Now what happens sometimes the manufacturer keeps the the GSM same or other parameters same, but he may, because of his own compulsions, may change a bit, like the pitch of the thread and something like that. Now suppose if we have certified the material considering the previous original material configuration, and if there are here and there small changes, overall the fabric is same but maybe the architecture is a bit different. So how is the scope of the certification changes, material certification changes? That I would be interested, because it's a very worrisome situation. So under such scenario, like how, so that I would be very interested if you cover this.
So first thing is, of course, manufacturer is not supposed to change anything when they're given the product which is certified. But if you are saying like some minor changes, and if there's a very minor change, naturally that what happens, there's a requalifying procedure.
Okay.
Of the material. And which is shown by the similarity. Of course, you not expect the major changes in the material properties. And usually what happens with the companies like Axel, when you're buying a material over the 10 or 12 years, there would always be some differences coming up, I can tell you, down the line. So, and whenever they're supplying a material with every batch when it comes to the factory, they supply the conformance report. And company also will check certain tests. Material meets the requirement always. So whenever the material comes, new supply of a material, or every batch, when it comes to the company, they will retest it. A few pulse.
Okay.
We have the qualification procedure. Actually, Yeah.
Okay.
So
Okay.
what happens, you will test tension, some important properties like compression,
Right.
and
Right.
some fracture toughness, if that is the property which you are interested in. So a couple of specimens, and the manufacturer has to provide certain test data
Okay.
also. So that is a procedure, of course, for the acceptance.
Okay. Okay. So you need not go for a like feature level test or something like you just on the coupon level itself you just prove that the material properties are not changing.
Yes,
So
that's right. Because
okay.
they are maintaining the same material. There's no reason for the changes to occur.
Okay. Okay.
But still, it has to be always verified whenever a new batch of material comes to the factory.
Okay.
Take a few coupons. That's the acceptance procedure, material
Uh,
acceptance. So what
right.
happens during when we are writing the specifications, we also provide the manufacturer the acceptance testing. So important
Okay.
properties like compression is
Right.
normally the important property.
Important. Yeah.
Yeah.
Okay. Okay. Fine.
So
Thank you.
that's but
Okay.
you don't expect them to change any weave or anything. They can't.
Okay, okay. Because sometimes we have experienced this, manufacturer, stitching is changed. The reason is unknown, but
Well, they can't.
sometimes,
The thing is, you as a buyer can always dictate. No, we cannot accept any changes to this
okay,
unless it's validated by the test data and which is not
test.
affected.
Okay, okay, okay. Thank you.
Yeah. And your question?
Yeah, one more, sir. Just an extension of the same discussion.
Yeah.
When we talk of manufacturing a huge aircraft and many number of them, do you always depend on a single raw material supplier, or you have multiple suppliers of same raw material, which you test and then, irrespective of whether it is a particular supplier or multiple supplier, you still can use them?
Well, that's a strategic issue. I can't tell about that, but normally
Okay.
what happens currently is a Haxel mainly.
Yes. But only?
Now, say Haxel is a supplier of the material, say for 787 program. And what happens? They will have an assembly line in Europe, one assembly line in USA, and say, suppose we were buying material from Europe, and then they switch the factory or another assembly line in, say, California. And that assembly line has to be again qualified. That is a procedure.
Okay.
So it's only the equivalence property you would try to evaluate for the same material, even though, say, Haxel, they have the same company, the same as similar assembly line, they will put another plant in some other different location. But in order to qualify that, even the process of manufacture fabric resin is same, but it's still, as a company, you will go through requalification of that company or the assembly line.
Yeah, my
So
question was, it is tricky to be dependent upon a single supplier in case there is some problem from that end. Then
the
we will be
issue,
stuck.
yes, issue with that is, suppose you have chosen one resin which is being made by Haxel. There's nobody else who is making that resin. What do you
Yes.
do? So you are stuck up with that.
Wouldn't there be equivalence?
No, equivalence means it's a huge cost to you. You can't.
Right.
It's a
Yes.
proprietary item. Suppose RTM resin being produced by Haxel. Cytec will be having their own different resin. It will not be
Yes.
same.
Yes.
So it's a very difficult situation. I understand. And probably aircraft companies might be struggling with that
Yes.
because of monopoly.
Yes, precisely.
So virtually Excel has a monopoly today.
Okay. Right, thank you.
So yes, I understand you would like to have multiple supplier, but really there's no choice in composites.
Mhm.
So I think Boeing also would be stuck up always with one company.
Okay.
Any other question?
Yes.
Yeah. Yes.
Yeah. Hello, sir. This is Avinash.
Yes.
You mentioned that most of the composite used in 787 is CFRP.
Mm-hmm.
It's just related to this topic, I want to know how do they select composite material? I mean, have Boeing arrived it at after doing some other material testing on composites it could mean that either CFRP is better than, let's say, glass fiber based composite or some other composite, or
Okay.
they do this, they give it to some other agency to do the material testing for them, and they simply use the material. So, do they have their own material testing system and everything, or uh, do some other agency do this?
I think you have to wait for my discussion. Say, if you see my presentation, you have got the presentation, all of you?
Uh, Presentation I
Hello?
have seen.
Yes, yes.
Yes, sir.
Okay. Now, say, I will be discussing that. It's a good issue. Good, say, here. Evaluation.
Okay.
If you see slide around material evaluation, maybe in your case, it might be around 135 or so. So material screening selection, all this building block approach. And what I need to, I'll be discussing this. How do you select the material and
Okay, sir.
what test you have to perform? So it is all covered. In fact, most of your questions, what you have been asking, are covered in my presentation because these are issues.
Okay, sir.
Any other question?
Sir, a question in general.
Yeah.
Myself, Dinesh. See, when we went through the curriculum, it was always told us that we will tailor the properties in the direction of the loading, and that's how we get a lot of benefit from composites as well. Like that was one of the other aspects of its superiority over the metals. That's what was taught.
Yes.
But in general, whatever I have observed, like this may be limited to my knowledge, but we end up doing components that are more like quasi-isotropic. So do you also
Yeah.
see that,
Yes.
or is my knowledge limited?
No, basically, it's most of the regions of a structure, suppose you skin, maybe around quasi-isotropic, 25% 0, 25% uh, 90, and 50% 45s. Usually, normally we use 0, 45 minus 45, 90 directions rather than having those funky like 10 or 20 or 30 degree or 35 degrees. No, that is what is not used. Conventional layups are used. Now, coming back to your this quasi-isotropic, yes, most of the region is quasi-isotropic, but some regions could be 10% zeros or for 80% 45s, where shear critical regions are there. So you will always tailor, of course, but there's always a limitation. You can't keep on changing from one region to another region the layups. There has to be continuity of the fabrics or the tapes layups. Mm.
Okay.
So yes, where suppose we are doing the spar design, uh, naturally you would require, say, web is more of a shear critical, so you would like to have the web layer to be around, say, 60% 45s or 70% 45 because of shear. So you are trying to bias, of course, a layup in order to suit your loading requirement. For skins, your span-wise loading is more, so you would try to have more tips span-wise 0 degree compared to the chord-wise. Or suppose a shear critical, you would like to have more of 45s than 0.90. So you try to optimize it, but there's always a limitation. And what happens in the load cases? In one load case, the same skin can behave in a shear critical or torsional. Another, when you consider bending, then you require more zeros in span-wise direction. And this is the optimization one has to consider. The loading situation. Unfortunately, what happens with the aircraft? There are different loading modes. One flight, it could be bending critical. Another flight, it could be torsional critical. Different segments of the flights. So you have to evaluate, in order to optimize these skin structures, what is my primary loading?
Okay.
So, of course, it's normally done, the optimization, but not to at the extent like optimization people will try to do. It's a limited amount of optimization.
Okay, sir.
Any other question? Yeah.
Thank you.
Any more questions? Yeah.
Sir, just general query. Have you shared this presentation with us, or will you share it at?
I've sent the presentation to Professor Dinesh and
Yes,
probably.
Avinash, and anybody else who has not yet downloaded it yet, you can go to the top on the team and you click on the files. Then you will get two files. One is the CV of Dr. Garg. The other one is the presentation file. So feel free to download it if you need it.
Okay.
Many people have already downloaded it.
I think it's interesting to download that and just glance through the presentation, because I've tried to cover a lot of material in this presentation.
If there are no further questions, I'd like to heartily thank Dr. Garg. Very patient answering of all the relevant questions from my students and colleagues. So thank you so much. It has been very relevant. If any of you have any feedbacks, there's one person who's raised his hand. Somebody wants to ask a question, please go ahead. You can unmute yourself. Okay. If any of you have any feedback, you have my email address, or through the chat, you can send any suggestions for the next lecture, and I'll pass it on to Dr. Garg. So Soumyadeep, you had something?
No, sir. No, sir.
Okay. Fine. Is there anything else that you would like to add, Dr. Garg, before we?
No, just.
Yeah. So we'll meet on next Friday at 3 p.m.
So you're Friday.
Yeah, Indian Standard Time.
Yeah, same time.
Yeah.
Okay, good night. Actually, for me, it's now good night, of course. For you people.
Yes, yeah, that's another thing I'd like to thank you for staying awake so late.
That's okay.
Our student schedules, because in the mornings they usually have classes, so we try to have it
that's fine.
very convenient to both
of us. It's not too late for me.
Thank you.
Course. Okay, good night, everybody.
Good night. See you.
Take care. And
good night, sir.
So if you have any question, please do pass on to me. Thanks. Bye.
Sure.
Bye, sir. See you.